And so it's really always good to have Jeff back and to tell us the latest developments that Watlow has to address this challenging issue. Jeff, over to you. Good luck. The floor is yours.
Thank you very much, Tim. This afternoon's presentation is based on some work that we did recently with Cummins. And we wrote an SAE paper and we presented that at the World Congress a couple of months ago in Detroit. So this is our paper, and I'd just like to acknowledge the co-authors, Dave Culbertson of Watlow, Magdi Kher of Mag Diesel Technologies, and Dr. Yuhei Zha of Cummins. This is an outline of what I'm going to cover, just a brief introduction to the company, Watlow, recap the industry problem statement, which we've been hearing about yesterday and today, point to some recent studies about the issue, give a description of our EcoHeat system, and then go through some engine testing that we did together with Cummins and what some of those results were, and then some conclusions. At Watlow, we are an engineering company nearly 100 years old, and we are the company that you turn to when you have a very difficult thermal problem to solve. And we are focusing our efforts of all of our engineers and all of our team members on those areas that will enrich the lives of others by applying our technology, whether it's purifying the soil, improving the quality of life, or in the case of diesel emissions, cleaning the air. We've been in the diesel market segment for over 40 years. And our products include things like engine preheaters that are used for large, high horsepower engines to enable a rapid startup, let's say in a power gen application. We also have high temperature sensors and other types of very rugged sensors for diesel applications. More recently, we've focused our efforts on exhaust heating technology. And we participate in pretty much every major market segment with the exception of passenger car. I felt like as I sat through yesterday's presentations and today's discussions that maybe this slide was not necessary because it's been talked about quite a bit. But really, the challenge is around how do we continue to improve the efficiency of the diesel engine while at the same time meeting tighter and tighter emission limits. And there's certainly a strong focus on CO2 reduction. Europe, I think, has led the way with regards to CO2 reduction and improving fuel economy. There's also this very important need to reduce NOx emissions, and we have coming legislations or regulations that are taking effect that are really putting pressure on that. And we have RDE in Europe. CARB is very seriously moving forward in the US with ultra-low NOx regulations. And then, there's always discussion about post-Euro 6 as well. So when we talk about reducing or improving engine efficiency, and we talk about reducing CO2, these things happen. Efficiency goes up, fuel consumption goes down, and when we burn less fuel, we make less CO2. So these are all positive things. But when we do that, we also have a negative impact, and that is the more efficient that we make the diesel engine, the less exhaust gas temperature that we have to work with, and therefore we have problems with enough catalytic activity to really lower the NOx. The SCR catalysts like temperature. When they don't have that temperature, we have issues to deal with. So this is really the challenge. And as the industry now is facing these next challenges, work is being done, technical studies are being done that indicate current engine-based exhaust heating measures are not going to be sufficient to meet the new legislations. One example of that kind of work is taking place at Southwest Research Institute. So CARB is sponsoring a program there along with MECA. And this work is being done as a technology demonstrator to show the engine manufacturers that achieving ultra-low NOx limits are possible. This first wave of work was done on a 2014 Volvo M13, 13-liter turbo-compounded engine, and various after-treatment technologies were applied. And one of the things that was important in that study was the addition of about 10 kilowatts of supplemental thermal energy. In this case, the mini burner was used to supply that heat, but they showed time and time again that you have to add some supplemental energy to the exhaust system if you're going to come anywhere close to meeting that 0.02 grams per brake horsepower hour limit. Last November, at the Integer Emissions Summit in the USA, we had a presenter from Navistar, and he showed this slide. And essentially, what Navistar has concluded is that if you're not up to temperature, sufficient temperature, within about 130 seconds on a cold start, you are not going to have the possibility of meeting the 0.02 limit. So that certainly raises the eyebrows. And he went on then to say that they are actively looking at additional thermal management measures in order to overcome that thermal deficit. And the technologies that they're looking at include burners and electrically heated substrates. At the World Congress a couple months ago, in the same session that we gave our paper, FEV presented a study that they did, and they did some modeling work looking for after-treatment technologies that would enable manufacturers to meet the Phase 2 greenhouse gas regulations and the coming ultra-low NOx emission standards for heavy-duty diesel. And they, again, looked at a variety of after-treatment system technologies and configurations, and they came to the conclusion that the use of what they called an advanced heating strategy, and what that meant was putting an electric heater in front of the DOC, showed from at least their simulation studies to be the most fuel-efficient means of meeting the low NOx standard and the greenhouse gas Phase 2. So we've been focusing our efforts on developing exhaust heating technology for those reasons. And we have a product that we call EcoHeat. And that EcoHeat system consists of an electrical heater, a resistive heater, and a smart power switch and control. And what it does is enables rapid and efficient heating of the after-treatment system. So let's first take a look at the electrical heater itself. And we have one on display here at our booth. You're welcome to stop by and see that. We have two diameters at this stage. One of them is 132 millimeters. The other one is 200 millimeters. And our intent here is to be able to cover engines ranging from about 4.5 liters to 15 liters. And so we chose those two sizes. And our goal is that the heater is placed inside of the customer's after-treatment system, whether it's in the inlet cone or it's inside the can, whatever the desired location is. But the heater is small enough and compact enough that it doesn't require its own separate footprint. It can be integrated within the existing space claim. And currently, we have 24 volt and 48 volt capability. To give you some idea of the heating capacity, at 24 volts, we can generate a maximum of somewhere in the neighborhood of 6 to 7 kW of thermal energy. And if we're operating at 48 volts, we can demonstrate 12 to 14 kW or maybe slightly higher. The other major component of the system is the smart power switch and control. The smart power switch is J1939 communications with the ECU, and it controls power to the heater and basically controls the temperature output of the heater as a result of the engine conditions that it is seeing on the CAN bus network. So what that amounts to is it maximizes the heater output during cold start and transient conditions, but it also takes care to avoid overheating the resistive elements and burning the heater up when the exhaust mass flow rate drops. Many of you who are familiar with electrical parts of engines, when you say, I have a 24-volt system, the alternator doesn't always give you 24 volts. Sometimes you have as low as 23, sometimes you have as high as 27 or 28. If we didn't have the smart power switch and we just had a resistive element, this graph shows how much in variation you could have in thermal output, anywhere from 3,200 watts to 5,000 watts, just by varying the voltages in the system. So the smart power switch then enables us to maintain a constant level of output regardless of what the vehicle voltage is. Again, this is 24 or 48 volts DC. So the smart power switch utilizes information from the ECU to control the heater. It maximizes the heating during transient and cold start conditions. All right, so I mentioned we did some testing with Cummins, and this was on their 6.7 liter ISB engine. It's a 2017 Cummins engine. It was fitted with a 2017 Cummins aftertreatment system, and that system was configured DOC, DPF, SCR, and then cleanup catalyst. And what we did for expediency here is we didn't package the heater inside the aftertreatment system. We fashioned some cones and we put the heater immediately out in front of their single module aftertreatment system, as you can see here in the diagram. Then we had a dynamometer, and we were able to load the engine and run it through various duty cycles. And then we had full emissions testing capability. This is a little bit closer view of what that heater looks like. So you can see we just packaged it inside of its own can and cones, and then we wrapped it with some thermal insulation. The heater was rated for a maximum of 6 kW. There was 2 heating elements inside of it. We had a 150 amp alternator, and we had a 27 volts DC maximum rating for that alternator. We had 2 batteries wired in series to make a 24 volt system. And we really did no integration work ahead of time with the ECU. So we just simply connected to the CAN bus network. Our power switch connected to the CAN bus network, and then they ran the engine through its duty cycles, and our heating system then went and actuated the heater based on what it was seeing on the CAN bus network. This is just one of the early test runs that we made. This was a semi-warm FTP, a semi-cold FTP cycle. And it's a little bit busy chart, but the first thing I'll call your attention to is the dotted red line. And the dotted red line was the target temperature for the DOC inlet, and that was 275 degrees C. The yellow line is the actual DOC inlet temperature. And then the black line is the power to the heater. And we limited the heater to 4.8 kW. And you can see then the other traces are engine RPM is the green line, and the set point and the heater outlet temperature are also plotted there. So we were able to turn on the heater quickly on this test, and the target temperature for the DOC inlet was reached at 260 seconds. The maximum heater power was applied was 4.8 kilowatts, as I said, and the average heater power over that first 410 seconds was 2.6 kW, and then after that only 0.9 kW. The total time spent above 2.5 was only 152 seconds. So the heater is able to provide thermal energy pretty quickly in the cold start, and the smart power switch limits the heater when exhaust mass flow rate is low. And you can see that where after the first, let's say the first 50 seconds or so, after the first hill, the green line drops down to an idle. And you can see then that the power switch dropped down to about 2,200 kilowatts, and that was because we didn't want to burn up the heating elements at that point. So this is looking at the current usage for the heater, and we have the blue line represents what the heater actually drew for current across that cycle, and the red line indicates what the alternator capacity was, and the gray down below represents what we made up for with the battery. So there were a couple of moments in that cycle where we had to tap into battery power, but if that's not desirable, the power switch can actually be programmed to avoid that. It can actually manage the balance between how much power is being drawn from the alternator and how much power is being drawn from the battery. Okay, this is an engine test cycle to simulate a road sweeper. So this is an example of a lower duty cycle real world application. So the road sweeper cycle has intermittent periods of higher load and then extended periods of idle. And we know that when we drop back down to idle for an extended period of time, the after-treatment system cools down. And you can see that this cycle here we are showing is for the first 8,500 seconds. Looking at the DOC inlet temperature then across that cycle, this is what that temperature looks like without any heating. And you can see that for a period of time, it does get above the target temperature of 275 degrees C. But then when that extended period of idle operation occurs, you can see how much temperature loss happened with the DOC. In comparison, if we look at applying the heater, the dark blue line is what that DOC temperature looks like having the heater turned on during that same cycle. So you can see it's a much less temperature loss during that extended period of idle time. And for most of the cycle, the DOC inlet is kept at the target temperature. This is a city bus cycle. And city bus cycles are another notorious real-world duty cycle where we struggle with emissions just because of what the engine is doing. So we have repeated starts and stops to pick up passengers and then go to the next stop. And so we have quite a bit of up and down in terms of engine speed. And we also then lose temperature in the after-treatment system when we go through those cycles. So this is the first 3,000 seconds of that city bus test cycle. Here's the same type of temperature information, DOC inlet temperature, and the target again is 275 degrees C. And with no exhaust heating, the temperature averaged just a little over 200 for that cycle, 208. With the heater turned on in that same cycle, we're able to keep the DOC inlet temperature right at the target for almost the entire cycle. So we had a little bit of heating time in the beginning, and then we were able to maintain it at the target temperature over that cycle. So the maximum heater power that we applied to do that was 4.4 kW. Very reasonable 24-volt capability with that kind of power on the vehicle. There's no need for any type of 48-volt system or beyond. So 4.4 kW. Average heater power was 2.3 kW. And you can see the difference that it made with the DOC temperature. This is looking at that same cycle and comparing engine out NOx versus system out NOx. So the dotted blue line represents what the engine out NOx was without the heater turned on over that bus cycle. And with the heater turned on, the engine out NOx is represented, cumulative NOx is represented by the dark blue line. So you can see we did make some incremental NOx by turning on the heater. We loaded the alternator. In turn, we loaded the engine. We burned an incremental amount of fuel in doing that, and we made an incremental amount of NOx. However, if you look at system out NOx, the dotted green line is representing what the system out NOx was without any heating. And that's directly a result of the fact that the catalysts were not up to the proper temperature. With the heater turned on, the system out NOx cumulative over the cycle is represented in the solid green line at the bottom. So you can see, although we made an incremental amount of engine out NOx, we more than cleaned up that and ended up at quite a low level of system out NOx. So the heater shows to be an effective means of helping to manage NOx emissions. Several OEMs have asked us the question, is there an optimal location for an exhaust heater in the aftertreatment system? And the answer that I always give is it depends. And it depends on really what is your strategy. You know, what are you working with for an engine strategy, engine calibrations, and what do you have for an aftertreatment system configuration? So just to illustrate, if you locate the heater pre-DOC, several advantages jump out at you. First of all, by having the DOC active, even at low duty cycle applications, the DOC is now lit and it's able to help us make NO2 and try to achieve the optimum 1-to-1 ratio of NO2 to NO to support the SCR fast reaction. We also then, by making that NO2, we also get a benefit across the DPF. We get some passive regeneration to occur. And finally, having the heater located in front of the DOC enables us to do an active regeneration from idle. And the mechanism for doing that is to light off the DOC with the heater and then dose fuel with a 7th injector or in-cylinder dosing, and you can achieve an active regen from low-speed idle. The disadvantage, of course, being further away from the SCR is there's a thermal lag. We don't get the SCR catalyst up to temperature quite as quickly, and we're not able to make as much of an impact on the urea dosing and thermolysis and hydrolysis reactions. Similarly, there are trade-offs by putting the putting the heater pre-SCR, faster heating of the SCR, but then we lose some of the benefits that we got by having the heater in front of the DOC. So again, my answer is it depends. I know at least one OEM is evaluating heat in both places and trying to figure out if there's an optimum by doing that. Looking at the potential benefits that can be derived from having an electric exhaust heater, whether your focus is on today's legislations, on trying to improve real-world NOx, or trying to meet future legislations like ultra-low NOx, there are a variety of benefits that the heater can provide. So you can get a fuel savings by enabling higher engine out calibrations. If you have an independent mechanism of heating the catalyst, that gives you degrees of freedom for advancing the timing of the engine calibrations, getting away from the engine-based heating, the exhaust throttles, the intake air throttles, and that's where the fuel efficiency comes from there. On the ultra-low NOx side of things, it's all about getting temperature and getting it very quickly, and having the ability to do that decoupled from the engine is certainly advantageous. So regardless of what your interest is, there seems to be some opportunity for helping with the heater. So in conclusion, the heavy-duty vehicle industry continues to make significant progress, improving efficiency, reducing greenhouse gases, and it's clear that there's still more work to be done. New thermal management strategies are needed to meet the upcoming emissions legislations. It's been illustrated that rapid heating is important to meeting the ultra-low NOx, and we also at the same time want to do that in the most fuel-efficient means possible. The EcoHeat system from Watlow fits within the aftertreatment system footprint. It can operate on either 24 or 48 volts. It uses the smart power switch to control the heater based on ECU information, so it's easily integrated with the system. And testing on the Cummins engine showed that even small amounts of supplemental heat can make a real difference. Just like to acknowledge all the folks that helped us at Cummins and at Watlow with this work. And with that, be happy to take any questions you might have.